So let's start. This is just a reminder what we've been doing last time. We've started a new chapter, number 4, which is a numerical solution of the Cauchy's problem for an ordinary differential equation. Let's review what the ordinary differential equation means. Suppose we want to find some function u depending on time, and the equation that defines it reads the first derivative of u by time is equal to some function f of t and u. So on the right hand side you have some non-linear, probably non-linear function f, which depends on both a simple variable t, which is usually associated with time, and our solution that we want to find. From the theory of ordinary differential equations that I hope you had in some form as a part of your previous education, it is known that the order of the derivative defines how many different, how many initial conditions we have to set to complete the formulation of this problem. Because this equation itself, it defines a whole set of curves u of t. It's not one curve. It is a whole family of curves that satisfy this equation. Okay? Do you know this?
No.
No, you don't? What about the family of solutions for this first order? What?
Derivative.
Well, the derivative is okay, but I'm saying the equation in this form, is it familiar to you? Suppose function f can be like sine of t plus u, for example.
I think yes.
Great. So we are looking not for a single value u, but for a whole function, the dependence of this u on time. It can be temperature, it can be concentration of some quantity, it can be displacement of some objects. Physical meaning of this equation can be very different, but the mathematics of it is the same. So it's not one function that fits into this equation, but if this equation has a solution at all, a whole bunch of functions can fit into this. And in order to select only one function, we need to specify its value at the 0 point of time when we start. And usually we are interested to know this solution in the interval from t0 to t. In general theory, this interval is said to be infinite. When we talk about numerical solution of such equations, we have to fix some value for t capital, because we are dealing with finite numbers anyway. So I'm saying that I have to specify some additional condition here, and this completes the problem formulation. Solution of such equations is a subject of another class, which is called solution of ordinary differential equations. It's part of mathematics course. Here we are not looking for an analytical solution. So analytical solution would look like I have to delete sign here because I'm not sure what the solution will be with the sign. But the analytical solution can look like, for example, c by exponent to some power. This would happen if our function f is a number multiplied by the function. Should I ask if you were taught to solve this kind of equations? So, do you know how to solve this kind of equations? If you have a derivative on the left-hand side and say lambda multiplied by u in the right-hand side, what should you do to solve it analytically?
Yes. I know.
How do you do it? Just explain if you can.
It's the derivative like that we are solving differential equation. Am I right?
Yeah.
And we have lambda u, so del over u lambda d and integrate over to equation like that.
Okay, so
Yes.
this is a separable differential equation. So you can separate unknown and known functions and then integrate. So du by u is equal to dt, and then you integrate over the interval of interest.
Yes. Right.
Okay, good. At least this part is known, is familiar.
Lambda.
Which gives us what?
Lambda.
Lambda.
Yes.
Right. Which gives us what?
Ln.
Logarithm, natural logarithm of
U.
of u.
Yeah, U.
Okay. Should
T over T naught. Or
lambda t.
okay. If we give
t0 lambda multiplied by t minus t0. Okay. And here
this is also.
Lambda u minus ln u minus ln u0. Okay. So no. Well, yes, correct. So what we usually do to simplify, so to say, this kind of equations, we potentiate it. So we put e to the power of the left-hand side, right? Logarithm u minus logarithm u0, and here we put e to the power of the right-hand side. Okay. And what's next? This is this can be written just as a product of two exponents, right?
Yes.
And here is what? Here is u, because we power e to the natural logarithm. Here is u.
U over u0.
U over u0.
0.
T minus t0. This is how we get this solution, right? So we found that c is equal to u0. Yeah.
Right.
Okay, good that we recall that. But it's not always possible to use some simple, or relatively simple analytical procedure to get this u of t. That's why we are interested in numerical ways of solving such equations. What do we mean by numerical ways? We mean that we introduce a mesh in our interval consisting of time moments tn. Tn is equal to t0 plus n by tau, where tau is a time step. t0, t1, t2, and so on up to t capital. And say we have equal time steps. This is our mesh. And what next? What's next? We have to approximate this equation somehow and obtain a finite dimensional problem that is in some sense close to the original differential problem. And last time we discussed the most well-known way to do that, the Euler's or explicit Euler's method, which is I will denote the approximate solution by another letter. If u is an exact solution, then I denote the approximate solution with letter y, and say that yn plus 1 is equal to what? Is equal to yn plus, I will not derive it again, I did it last time, yn. So, are you familiar with this as well? This approach as well?
No.
How we obtain that? We can, in order to obtain this equation, we can integrate again the original equation, du by t, integrated by time, and integrate the right hand side as well. So now I'm just repeating the material of the last lecture. What do we get here? So integrated from time tn to tn plus 1. Supposing that we already know this guy, the approximation to the solution on the previous step, so we want to know the approximation on the next time step. And here we get what? U of t n plus 1 minus u of t is equal to this integral. And we can do nothing with that because we don't know the how f is looking. And after that, we can approximate this integral using some method that we already know. And we discussed that one lecture before. Those methods one lecture before. For example, we can take a method of left rectangles, which means that we approximate this integral, and now I'm starting to write approximate relations. We approximate this integral with the distance of the interval multiplied by the value of function on the left hand side of the interval, of sub-interval, so which means f t y n. This is how we obtain this expression.
Yes.
And using this general approach, we can obtain many other alternative methods. One of them we discussed last time again. If you take here an approximation using the right rectangles, yn plus 1 will appear on the right hand side. And tn plus 1 will appear here, right? Instead of tn and yn. Which means that this simple formula becomes not that simple. Implicit Euler. I have to repeat it anyway. 1 plus 1 equals yn plus tau f of tn plus 1 yn plus 1. Can you use this formula to get yn plus 1?
Yes.
How?
To get yn plus 1.
Yes. Yes. If you want to know this guy, and you already know this guy, and you already know this guy, and you can calculate this guy, but you cannot calculate this guy.
But here also, yes, yn plus 1, yn, yes, we put it here, over there.
Well, you know this, so you can put it here and calculate the value of this function.
Yes.
But the situation has changed. You do not know this value.
Okay.
You don't have anything to put here to calculate the value of function f.
Okay.
How do you get yn plus 1 from such type of formula?
Just like as you know the last second equation. You see, yn plus 1 minus yn equal to tau f tn.
No. It's a different method. We stopped here. We stopped discussing the previous method here.
Yeah, but
this is a different approach. This is another method.
Okay.
And we have to deal with this expression. We don't have this any longer.
Okay. So
My question is how to get a solution from this formula. It is not explicit. It is implicit. Because the unknown is involved in both parts of the equation.
Yeah.
But I hope you were taught to solve nonlinear implicit equations numerically. It is called, well, if you put everything on the left-hand side,
Right.
if you don't understand it now, you can review the previous lecture. I explained it to Alexandra last time as well. So, if you put everything on the left, you will get some function phi capital of yn plus 1. And the equation will read like this, equals to 0. Which means that we want to find such value, it's a single value, one number, yn plus 1, that being substituted into phi capital makes it 0. And, or in other words, phi capital, if we consider it as some procedure that takes a floating point value and makes something else from it. Let's look at the phi as some procedure and call it operator, in mathematically speaking. F is an operator. So, we are looking for a stationary point of this operator. What means stationary point? It is such point that the operator cannot move anywhere. It stands still, and the result is 0. Well, it's not. I'm not exactly correct when I'm saying that. Not this operator, but if we form another operator, 1n plus 1 equals f capital of y. We can reformulate this problem in this form. How we do that? We can, for example, say n plus 1 plus tau phi. If this guy is 0, we get the right equation, the right equality, right? If this guy is 0, and we want this guy to be 0. So I'm saying that this formulation is equivalent to this formulation, and then our unknown solution is a stationary point for this operator f. I called f this formula to be f. It is f of yn plus 1. Okay, new operator f is just this formula. And this guy we know how to calculate it. We just move everything leftwards. Okay? So, our unknown solution is a stationary point of the operator f. Because operator f cannot do anything with this point. It acts on this point, but the point stands still on its place. And there are a number of methods to solve such problems. One of the methods is a stationary point iteration method. Stationary point iterations. In Russian it's called метод простой итерации. Слышали про такой? Вам вообще на каком языке преподают? What language you're in English? Okay. So is it some American university of Central Asia?
Like this.
I'm familiar with this university because I worked with a student from that last semester. Okay. So one of the possible approaches is the stationary point iterations method. Another approach, also well known, is Newton's method. So this says that we know how to solve this kind of problem, but there will be much more work as compared to this situation to get our yn plus 1. And last time with Alexandra we discussed why people bother applying this approach instead of this approach sometimes for some problems, if it takes so much effort to get yn plus 1. This approach is better for some special kind of problems which is called stiff problems. And ideally we will talk about stiff problems a little later. So this method still has its own applications. Okay, let's talk about another approach. If we used the left So suppose we know approximation for our function up to this point Tn, and we want to go further. We have this integral, or this integral form of the problem, and we start from here again. What are other methods to approximately compute this integral? What are some other methods? Do you remember? We discussed it 2 weeks ago.
Other methods?
How? Two rectangle methods we have just recalled. Left rectangles, right rectangles, what else? Trapezoidal rule. Do you remember? Trapezoidal rule. So, we don't know it, but we can approximate it with a trapezoid. This part, right? So take the value of function here, take the value of unknown value of function here, or function f. And compute, or at least write the formula to compute the area. Let's do that. So yn plus 1 minus yn is equal to trapezoid. What is the area of the trapezoid?
Here, Tn.
Tau.
Tau. Multiplying.
By what?
By, what is this y here?
It is our approximation to the unknown solution u.
Yes.
So this guy we know, this we want to find.
Yes.
So how to approximate the integral, this integral? What should I write next if I want to use a trapezoidal rule?
Yes. If you want to write this, f multiplying Tn plus 1. Or
You mean f of Tn?
Yes.
Is that what you write? So you want to compute f here, Tn plus 1 you said?
Yes. And here then Ft
and also it depends on the second argument, right?
Right.
So we have to compute this argument at the same point.
Yes.
Okay? And what else do you need to compute the area?
Yes, the second one plus Ftn.
Yeah, correct. Ftn yn. Okay? And something else, some coefficient. Over 2. This is how we get another approach, another formula, which is also implicit as the previous one, because the unknown solution is involved in the right-hand side as well as in the left-hand side. And we repeat our story about the stationary point methods or Newton methods to solve it. It's possible to solve it. The message is that. So, last time, again, please watch the video, we talked a little bit about the approximation properties of this formula. How well it approximates the solution. What is the error of this approximation? We can deduce the error from recalling the error of integration. So, approximate integration is associated with some numerical error, always. And if we recall what the error was, we can understand what the error will be in this method and in this method. Yeah. And if we do the analysis, which I'm not going to repeat now, we will find that this error is of the order O capital of the step of our mesh to the first power. Yeah. To this guy, implicit Euler, for this guy the error is also of the order of t to the power of 1. even though it is implicit, it takes so much effort and so forth, it's still on the first order accurate. So the accuracy, there is no accuracy gain if you take this method. But there is a stability gain. How about this method? How can you find this O of t to some power at all? The procedure was discussed last time again, but I will just remind you and those who will look at this video. What we do is we expand our exact solution at the point where we want to know it, the new point, in the vicinity of the previous point. So we take a derivative, compute it at the previous point, and multiply it by time step. Plus you doubled second derivative at the same previous point by t squared plus, and so on, but here we can say O of t cube, O capital. Have you been taught O capital and O small notation on mathematical analysis? Was this notation used?
No.
O capital is the same order as the value in the parenthesis, the same order. So if I have tau to the power of 2 here, yeah, I will have tau multiplied by some constant to the power of 3 and higher order components. Okay? There is an alternative notation, U small notation. If I wanted to use U small notation, I should have written this guy here, because U small means that higher order components than the one written in the parentheses. So you have to differentiate between O capital and O small very carefully. In mathematical analysis, they like O small more. But in numerical analysis, it's more convenient to have O capital here. Okay, so you write this expansion, and the next thing you do is you compute the error at the point of interest. Or better to denote it with E, not epsilon. I will say why it's my notation. Minus yn plus 1. You just subtract your formula from this expansion, and if you do that, you will find, and when you do that, you have to also recall that the first derivative at point tn, according to this equation, is just the right hand side computed at this point. Okay, so we can replace the second derivative taking the first derivative of this f. Okay, and so on. So this will be expressed via f. We express everything via f. Then we subtract approximate solution from the exact solution, and we'll find that some of the components of this expansion are exactly reproduced by this formula, to some order. When we subtract one from the other, we get zeros. 0 by t to the power of 0 plus 0 by tau to the power of 1 plus, for this particular case, we should find that the order of remaining this is 0 and this is O to the power of 2. For previous methods, this was not 0. For the previous two methods, this guy was not 0. For this method, this guy will be 0. And this guy remains non-zero in general case. So we say that the trapezoidal rule has has the accuracy of the order of O to the power. Yeah, okay, this is correct. What I've just said is correct. Because I didn't say another part of the story. Usually the story is continued and this exercise is done to the end. And if you do that to the end, and if you assume that the solution is known exactly at the previous point here, at the point Tn, then you will see that only O of t to the third power remains. But if we don't make an assumption that at the previous point we knew the solution exactly, if we don't do this assumption, then we will have a remaining term with the second power of tau. It is important, that's why I'm putting so much effort to explain. So, it says that this rule is better in terms of accuracy, in terms of the accuracy, because the smaller step we take twice smaller step, and we get how many times better solution? If we reduce our time step tau twice by a factor of 2, what's going to be?
4?
Yes, we get 4 times more accurate solution. Here we made our step twice smaller and we got the solution twice more accurate. Here 4 times more accurate. It is better. What else? But this method is not very convenient because of its implicit nature.
Yeah.
How to make it convenient?
To solve the implicit function.
We don't like solving implicit problems because it involves programming a simple iteration method which is not very fast, or a faster Newton method which requires to take derivatives of some functions. You have to take derivatives to implement it.
Maybe we use another method.
Well,
for this method.
We can combine 2 approaches. We can combine this implicit approach and this explicit approach.
Okay.
And the method will be named Heun's method or Cauchy Euler's method. So what we do? We calculate the first approximation or zero approximation to the solution on the next time step using the Euler's method. And then we substitute this approximation to this formula to the right hand side and get a better approximation to the solution. Plus tau by 2. I will write them in inverse order to make it more typical. Plus what? Plus f of Tn plus 1, comma, and we just substitute this whole formula here. I can write like this, but what people do is they actually substitute it here. So it is like the stationary point iterations method actually. It is exactly the same what we would do if we implemented the stationary point iteration, but we would continue in that case. We would use this first approximation as a second parameter here again, and get the second approximation and so on down to the convergence. In Heun's method, we don't do more iterations. We just use one step.
Okay.
And as a positive result of our actions, we get explicit method first, and this method will deal with the second order. Explicit and second order. It's a win. We won.
Okay.
There are some things to say about the stability of this procedure. It is a little bit worse than the stability of this guy, but it's convenient and very practical. If you want something very simple and you don't want to deal with more complex procedures, you just take this Heun's method and go with it. По-русски это будет метод Хойна, а также иногда пишут Хьюна. Ну и еще Эйлера Каши. В разной литературе по-разному. Okay.
And Cauchy-Euler's method is another method, or it's the same?
Cauchy-Euler's method is just another name for the same Heun's method. Just another name. I'm giving you two names to let you recognize it when you read some literature. If you need to solve the problem of this kind, you will read literature and probably you will find this same method under a different name. Okay, and I wanted to introduce another interesting procedure as well.
But I have a question about this. We saw how we can solve this equation. We should know how to solve this implicit equation. After that, we can solve this.
Well, no. Again, let's look at this. Here, what do you know in this first formula?
Yes.
You know this.
Yes, explicit.
You know this.
Yes.
And you know this and this. So nothing prevents you from calculating this value, right?
Right.
It's explicit.
Yeah.
Then you just substitute it here. This was the point of problem for us.
Yeah.
Because we did not know what to substitute here, and now we know. We know this number. Just put it here.
Okay.
This you can simply calculate Tn plus 1 plus tau. This is Tn plus 1.
Okay.
Right? Okay? So you know everything on the right hand side again, and you just get the next approximation explicitly.
Okay.
No need to do any iterations for okay. One note about all four methods that we've just discussed. This is number 32, y2. I'm not sure why I write 2, because it should be 3, and this should be 4, because this was 1, this was 2. Okay, so we have discussed four methods, and all of them have one common property. They use only the previous value of the approximate solution to calculate the next value. Only one value.
Yeah.
Neglecting the fact that we have previously calculated yn minus 1, yn minus 2, and so on down to y0. So to say, we have this value, or can have them, without additional expense. So the natural idea is to employ this fact and use previous values to improve the accuracy of the method.
May I take the photo or no need for that?
Yes, please. I'm taking videos, but if you like, you can take photos. Sure. Okay. Okay, let's discuss another method of a different family, from a different family. I will delete this guy. This guys. So, am I saying something new for you at this point?
Yes?
Okay. Just want to make sure that I'm not repeating information that
No.
everyone already knows.
It's a lot that's useful for me.
Okay. Okay, so 3.5. If you look at the original equation again, what we've actually done, we integrated it, right? But we could do, or could use another approach. When we integrated it, what we actually obtained on the left-hand side. We can look at the left-hand side using an alternative way. To here and down here. If I divide all the approximate equation by tau, on the left-hand side I get something which is called...
Logarithm?
No. These are two values of the unknown function in subsequent points divided by the distance between these points.
Velocity?
Yes, physically speaking, it is an average velocity during this time from Tn to Tn plus 1. And mathematically speaking, if we tend this tau to 0, it is going to be what? It's going to be derivative of the function y by t, actually, by t. So we are approximating the derivative, staying on the left-hand side. How do I want to call this method? Well, improved Euler or Nustroem method of second order. So you can directly work with the problem of approximating this derivative without integration or anything else. Let's do that. Let's use the central difference expression to approximate the first derivative. How it reads the central difference approximation. Do you remember? From our two lectures before, we talked about that. Derivatives approximation.
Yes.
Yeah. So I want to compute the derivative sitting at point. I want to compute the derivative at t plus 1. Second. Yes, this is Tn, this is Tn minus 1 then. And I want the derivative at this point, actually. At this point, at Tn. Using the central difference. So, what do I write?
Tn plus 1 minus Tn.
Y. N plus 1, y.
Yn.
And minus 1 if I want to use the central difference to compute derivative at this point. Okay, central means I go to the left and I go to the right, but the very point is not involved. Is not involved. So divided by what?
T.
By what?
Tn.
No. Tau. Tau should be involved here.
So.
But how many tau? Tau.
2t.
2 tau.
Right.
2 tau, because this is the distance of the whole interval, right? This is the approximation of this first derivative using the central difference formula. And on the right, I can take my function at the very point where I'm sitting. F of t n y n. And this is how I get the formula of this method. Let's rewrite it in a form that's probably more convenient for the practical application. -1 plus 2 tau f tn yn. So, what do you notice about this formula which differentiates it from the previous formulas? You know the y0, which is equal to u0, actually, you know how to start, and it was sufficient for all previous methods. For all previous methods, you just need to know y0, and that's it. For this method, what's happening? How to start?
If we n equals to 1, or n to...
How do I start? I want this guy.
T1, yes.
Can I use this formula to compute T1? To compute y1?
T1.
Y1.
Yes. Y1 equals to U0 plus Tf. 2T F.
Really? Let me see. Y1 is equal to what? Did you say?
U0.
Y0.
Y0 equals to U0, you say. Okay.
If I want to have 1 here, I have to set n to 0.
1.
N?
Y2. It's a Y2.
Oh, Y2 is okay. Y2 is no problem. So, what I should write here?
Y0.
Y0, and that's fine.
0, 0. It's not.
Oh, you want y0, yes. Okay, got it. Plus. T1, y1. And I have a question to you. What should I put here?
So we should find y1?
Yes, where? I don't have it under the table.
Do
you? So, how to find y1?
Okay.
Can we find y1 using this formula?
Yes.
How? You tell me, I will give you a prize.
Y1 is equals to y minus 1 plus and 2 tau.
It's very interesting. What do you mean by y minus 1? Can you tell me? Where should it appear from? I start here at T0. I don't know anything about the previous, about the history.
Okay.
I don't have this information at all. How to start?
Okay, maybe if we put no.
Well, this is a real problem with this type of methods. You have to obtain more than one initial value. This additional initial value should be obtained in some other way before we can start.
Okay.
For example, we can use Heun's method, right? Because the Heun's method is a one-step method. It uses only the previous value of yn. It doesn't go beyond yn to the history. And this is very good. So we can use Heun's method, but not to obtain this value, better to say to obtain this value. Use another method to start. The only watch out should be this method is of the second order. So the method that you are using to calculate the starting values must not be worse than the method that you are using here, the multi-step method that you're using here. Otherwise, you would spoil the accuracy at the very beginning. And spoiling the accuracy at the very beginning is awful, because all the next values will involve the error that you have introduced in the first steps. Okay? That's why the method that's used to calculate the starting values should be very good. It should not be worse than the method you're using. But if you found the way to start, you gain accuracy for nothing, because you need to calculate your function on the right-hand side only once per step. Only one calculation of function. Here, for example, you had to calculate this f how many times? 1, 2, and 3. Right?
Right.
3 times per one step, for one to calculate one new value. And here you have to calculate your f only once. This is very good from computational efficiency point of view, and this is very good from accuracy point of view, but you have to start somehow. These examples, let us classify the method, classification. Methods can be one step or multi-step. Do you need a break?
No.
Okay. And we have to reserve time to discuss your assignment, right? Okay. So we've considered the most important basic modifications of the Euler's method, and we've introduced the idea of the multi-step methods. So these are two big classes, one-step methods and multi-step methods. And I should say that after Euler introduced his method in Euler's method 3.1 was introduced somewhere in 1775 approximately. After that, it was just used, and not many people solved problems that required application of such methods, probably only those who wanted to calculate the trajectories of the planets. And for this particular problem, calculation of the trajectories of the planets, the Euler's method is just awful, because it accumulates error very quickly. And instead of the correct trajectory, you very quickly get something absolutely different, which goes far from reality. The explicit Euler method, I mean. In the middle of 19th century, Adams, British mathematician Adams, has developed a set of improved procedures to improve accuracy of the Euler's method. And these procedures were all multi-step. So they used the idea of subsequent usage of the previous values of y. And they were heavily used to calculate the trajectories of the projectiles in ballistics. So the guy who asked Adams to work on this was Bashforth. That's why this kind of methods is usually called Adams-Bashforth methods. In explicit multi-step procedures. But you can see how much time elapsed from the initial development of Euler's method to the improved version. And only at the end of 19th century or beginning of the 20th century, the development of these methods has taken place. And this is our next topic of discussion, actually. But before that, I wanted to give you one example in the form of a table, practical example, to let you compare how accuracy of different methods compare to each other. This is an example I took from a book, so it's possible to find it, or just to reproduce it. And we'll do it. Let's see how accurate are different methods. And if you are tired, let me know. We'll stop. Are the teachers in your university all English speakers, or you have local teachers from Uzbekistan or somewhere else?
You have also local teachers, also foreign teachers. Especially in the master's degree, just opened this year in our university, so that's why a lot of teachers are local.
I see. Okay. So 3, 6. Well, let's make it blue.
Every time in our university has also numerical methods. It's like another professor, it's foreign professor, Rosella.
From where?
Huh?
From where do they come to
I
Uzbekistan?
don't know, but
Oh,
it's
don't know?
not now name of Rosella.
I see. Okay.
Indian something.
So, an example. To compare accuracies by naked eye. Compare accuracies. Let's take this problem. U by t is equal to 2t minus 3u. At the initial condition of this form.
Can you change your master?
Okay. I was thinking about it, but I didn't do it. It's wet. That's why the marker doesn't write very well.
Maybe
Must dry out a little bit before you can write. So the exact solution of this guy is minus 2 over 9 plus 2 over 3x, or not xt, plus 11 by 9, e to the power of minus 3t. Sorry. It's an effect of rewriting things from the book to write notes. X appears on the places where t should be. Okay, so I will just show the results of various methods application at these conditions. So we are computing down to the time 0.2 seconds and at time step 0.1 second. And the methods we are looking at are the following. Explicit Euler, Implicit Euler, Trapezoidal rule, Heun, and improved Euler. I don't like this name, this method, because it's not well-established name. Sometimes it's called Nustroem method, sometimes maybe even Mills method. So, in various books, they use different names for the same thing. Okay, so approximate solution. approximate solution which approximates exact solution at this time point, and this is the delta between the approximate solution and the exact. U minus 2. So 0.51, 0.6343, 0.788, Heun is 0.5895, 0.587. And the error which we are interested in the most is this. This is the absolute error. Absolute error. Minus 0.008 and minus 0.005. So you can see one order of magnitude for these guys. Just because they are all second order methods. Just to look at this and feel before you try it yourself.
Okay, if we have like error is the little, so that's why you have a clear equation.
Not sure I understand your idea. Could you say it again, please?
That I'm saying if we have like error delta is more little, so that's
smaller.
why
The error is smaller.
It's smaller.
Then
So you have a clear equation.
Clear equation? What do you mean? A clear equation?
Accurate.
Accurate, yes. Well, it's not the equation which is accurate, but the approximation for the exact solution is more accurate. So the curve, if we plot it, why did I write t here? What did I mean? It's no, my mistake. Should be 1. So at 0 time point we have a value of 1 for the exact solution, and then this exact solution goes somehow at t, if t equals 0, let's think a little bit. So here we have 1, here we have 0,
Right.
1, and
1.
should be 1.
Right.
Is it 1?
Yes.
Okay. And then if t grows, it is almost linear, but we have this exponent, so it should be like this, little curved solution, if I'm not mistaken. And the approximate solution, let's imagine how it would look. We are looking at the point t2, right? So using Euler's method, what the Euler's method would do, it would approximate the tangential line. Tangential line from here to here. Then it will compute the tangential line again, like if it was here but shifted downwards, tangential line to the actual curve at this point. Here, and then here, and so on, but we are only looking at this point now. So what the implicit Euler would do? Approximately the same thing, but it is implicit, and this point will lie much closer to the original curve. Closer, closer, closer. And all other methods are a little closer or a little farther. Well, actually, I didn't do a correct plot, because the implicit Euler is not much better in terms of accuracy as compared to the explicit Euler. It will go somewhere around here, maybe a little bit better, but you can see the value. It's almost the same by absolute value. No big improvement. As for the other methods, they will have much better accuracy. The curve will be much closer to the unknown exact solution. Okay. Let us maybe introduce a general classification of the methods. We have already discussed what the one-step means, what the multi-step means. Let's formalize it. I don't want to do it without. We're speaking for 1 hour already. Are you okay? Still able to understand what I'm saying? Because 1 hour is is a lot, actually. 1 hour is a lot. Well, let us introduce the classification and maybe stop at this point for today, because otherwise it's going to be too hard for you to understand, and I need to reserve some time to talk. Paragraph 4, general classification of the numerical methods, approximation, and well, yeah, I have to introduce it here. No. It doesn't work any longer.
Okay, you wait.
I have a number of pencils with me. Approximation, convergence, stability. Okay, classification is the following. So if we have a problem star, we can write a general form of our methods. We've seen that all the methods that we've considered up to this point had these two elements on the left. Or we can put this element on the right. It doesn't matter much. We can move, but we can think of the other ways to approximate the derivative that involve more points to the history, going to the history, right? So alpha, what's going to be the index k minus 1, n plus 1 minus k minus 1 plus alpha k yn plus 1 minus k. This is the general form of the expression, finite difference expression, that approximates this derivative. And on the right hand side we should have the time step first, and then some approximation of the right hand side. For the 4 methods that we've already considered, we've seen that what we do is we calculate this function at different points. Or probably we substitute this function calculated at other points into the second argument, right? Like in Heun's method. So, generally speaking, it's going to be some function phi capital depending on the previous time step and previous values, previous computed values of the unknown up to this, and maybe even this. We've seen this already, right? And what else? And it also depends on the time step. Oh, well, if it depends on the time step, I should do the time step from here. Okay, so this is the general formula covering most of the methods that are applied to this problem, ordinary differential equations, Cauchy's problem. So, if we assume that alpha 0 is not equal to 0. Alpha 0 is not equal to 0. Okay. It's possible actually to think or to consider methods where on the left we don't have the new time value. It's going to be the methods called like backward calculation methods, but they are rarely used. So let's assume that this coefficient is non-zero to let yn plus 1 remain on the left-hand side. And also, we can have two situations for this guy. If phi depends on n plus 1, the methods are implicit.
Okay, we will use implicit method.
And if phi does not depend on yn plus 1 and only depends on yn or previous guys, then, well, I shouldn't write like this. I should write like this.
Okay.
Explicit. And also we have a parameter k here. K is more than 1, more or equal to 1. K is the number of steps of the method. So if k is equal to 1, one-step method, if k more than 1, multi-step method. And that's it about the classification. And let's keep the rest of the material that I have. Probably I will sit down and write you and record a video for you to watch offline.
Okay.
Of the next part, because we need to actually to move on quicker. Otherwise, we wouldn't cover important material that we intend to cover in this course. So probably I will send you a separate video with the next part. And let's stop here for today.
Okay.